you're in the right room. And this is actually pretty encouraging. We have an actual room. I really like looking around the schedule this year at JavaOne and seeing how many GC talks there are. And it's kind of amazing that after all the other GC talks, you're still here. So we'll see if I can actually teach you anything new or different or add any value there. But this is a talk that tries to explain garbage collection as a field, how it works in general. The general purpose of the talk is to educate you on garbage collection, for you to understand not what client does what and which collector you're choosing today and how to tune it exactly, but more importantly, for you to understand how garbage collection in general works as a machine, in the various options and forms and algorithms we will use, and then to actually be able to use what you learn yourself and think about how the mechanisms work, understand the fundamentals, and then read up and learn the various collectors and flags you might use and use that understanding the machine. I find that as in all fields, understanding the basics and working from there is very useful. I promise that I'm very, very proud of the garbage collector we make at Azul, and we think it's the best in the world. That actual bragging will only come at the end. And I do have a hidden agenda here. I'm going to spend most of this talk educating you on the fundamentals that let you understand why your garbage collector is the best one. Okay. So a little bit about me. And I know a lot of you probably have already seen this slide, but I do repeat it. I'm the CTO of Azul Systems, one of the co-founders there. I've been working on different ways of doing garbage collection, different than the common directions and trends in the industry for over a decade now. And actually built the POSLESS and the C4 garbage collector algorithms. There are academic peer-review published papers on them. And this is some evidence of me actually working on garbage collection. This is in my kitchen in 2004, and that is, for those of you who don't recognize it, that is a trash compactor. And there are fragments coming out the back because the compaction wasn't working well, and it stalled. It paused. The mold is present. You see it stalled, and we had to fix it. So I took out the garbage bin and book and looked for some ideas there. That is not exactly how we came up with C4. I've also worked on a lot of other things, everything from drivers and operating systems and helping design hardware even. I got an instruction in the CPU called, I got to select the name and I chose get immediate long. If you think about that. And I've built big Java systems to manage millions of subscribers in telco environments across hundreds of servers. Built firewalls and traffic routers and switches. And I've been doing Java virtual machines and garbage collection, things like that for the last decade. So I've made a lot of mistakes, and hopefully some of them will teach others that people things too. I'm also a member of the JCP Executive Committee, and I mention that really only because we're running for election again. So remember, just like in a couple of weeks, we actually have an election, so if you like this, look it up. About Azul, where I come from, the company I started, we focus on building scalable virtual machines. That's all we do, Java virtual machines. And in order to do that, we've had an approach for a decade now of doing whatever crazy thing it might take to do that. That included some pretty crazy things. We built custom hardware with custom chips and custom CPUs and custom instructions. This is a picture of an 864-way SMP with 3/4 of a terabyte. And given that this was 2007, that was pretty impressive. But we don't do this anymore, or at least we don't design these anymore. We still sell them to people who buy them. But all of our design is no longer focused on hardware. About 5 years ago, we looked at the commodity x86 roadmap and said it's getting good enough. We don't have to make our own hardware anymore. We can now do on pure software on commodity hardware, what we used to need this kind of thing for. And the beta is our legacy, our current and the future is pure software. And that's something we call Zing. It's a JVM for x86. We're also known for low latency, consistent execution, small large data sets, everything we need. But enough about that. Let's talk about the talk. At the high level, I'm going to cover fundamentals. We're going to talk terminology, metrics, background. We're also going to cover classification using those terms and that I will define, hopefully precisely, and look at actual commercial collectors available today and actually classify them using actual garbage collection terms. And then I'll introduce you to a problem I call the application memory wall problem, why stop the world is actually a problem, and why everybody seems to be working on it. And also go to an actual, what the world looks like when you solve it with something like our C4 collector. Before we get into details, I'd like to do a quick poll. I do this at almost all talks that I do, and it is simple. I assume you guys all are here programming in Java to some degree, or in here in the road show. The other one down in the swim center is for the other people. I want to go through the room and see how many of you program in applications where your instance of an application has at least 1/2 of a gigabyte of memory. Please raise your hand. That's a lot of you. So, how many of you use at least 1 gigabyte of memory? Yeah, about the same. How about more than 2 gigabytes? Almost the same, starting to lose some people. How about more than 4 gigabytes? Now look around, starting to drop. But keep your hands up if it's more than 4, okay. More than 10. More than 20. Okay. How about more than 50? Cool, so I have something to sell you. We look for that in the room, right? But let me show you how smart I am, okay? Ooh. I guess that this is where 80 to 90% of the room will be, and I guess that because every room I've spoken to has the same pattern, pretty much, except when I get all you guys together normally. But keep this in mind as we talk through this, because I will come back to this subject. It's very important for the industry as a whole. Notice that I didn't ask any of you what you do. I didn't ask you what kind of application it is. I didn't ask you if it's big data or search or an app server or a trading system. And it's surprising that we have such a tight grouping or in all those. Okay. So why do you need to understand a little bit about how garbage collectors actually work? A lot of people say, well, the magic is there to make it so I don't have to think about it. And to explain to people why there's some motivation to really understand what the machine sort of does, I use an actual story that I call the story of the good little architect. This actually happened. I actually ran into it. Anybody here like Mark Twain? That's what the reference is to. And I define a good architect as not somebody who can build good architecture or good code necessarily. It's probably a plus if they can do that. But first and foremost, they must be able to impose their will on a team of people and get a team to do what they decide rather than just themselves. If they can't get that done, they're not an architect, they're a philosopher. So we met a very good architect about 6 or 7 years ago when, using our Vega appliances, we had what we called the automated pauseless collector. And that pauseless collector was pausing for 18 seconds on an application. So we obviously wanted to find out what's wrong there and how that's happening. And when we investigated, we found that this specific application was performing tens of millions of finalizations in every GC cycle. And at the time, our concurrent collectors were still doing finalization as a stop the world event, because come on, how much of that is actually getting done, right? And here there were tens of millions of them stopping for a really long time. Now this was not normal, so we went to figure out why this is happening. And we found out And by the way, we did fix that since, Zing, since does, even then it wouldn't pause. But we found out that every single class written in this project for a period of 18 months had a finalizer. Every single class, anybody in the building wrote had a finalizer. That's the sign of a good architect. Very good architect. None of them escape. Now, some of you probably understand why this is funny, but the finalizers were nullifying the references and doing nothing else. This is all the finalizers were doing. They're putting nulls in every reference so that before the object dies, it'll make sure it doesn't refer to anything else, because that will probably help the garbage collectors do less work. Now, here's the thing to understand. This is a fundamental issue of whether or not this is a good idea. It's not a good idea, okay? But why is it not a good idea? Because you're in Java and you're not in C++. This is exactly the right discipline for C++ destructors. Guess where the architect came from? If you are building a large C++ project, you better have this discipline or you will have memory leaks. So that discipline is necessary. However, destructors and getting rid of reference counting in C++ does not translate to finalizers in Java. It's the closest visual thing. In Java, it's the opposite of what you want to do. It's the worst possible thing you can ask the collector to do in order to try to help it, and it doesn't help it at all. Hopefully, at the end of this talk, you guys will actually understand some of the why, or maybe more of it. So, I use this as an example. Much of what people think they know about garbage collection is actually wrong, and is actually, GC is actually much better than you think in many things, and it's much worse than you might think in others. So for example, GC is extremely efficient at allocating and managing memory. By far, with nothing even close to it, there is no faster way to allocate a free memory than GC in a computer today. This might sound controversial. I'll show you exactly why the math works that way. But there is no more efficient way. Malloc and free is dramatically slower than with GCs. It spends a lot more power, a lot more cycles, a lot more everything. Most people don't think that's true. Dead objects cost us absolutely nothing to collect. All current modern garbage collectors spend only time thinking about live stuff, not about dead stuff. That's where efficiency comes from. And garbage collection will absolutely find everything that is dead. It doesn't need help. It doesn't need you to break your circular list so nobody will find the other end of it. If it is dead, it will be found in all modern JVMs and all modern collectors. Now, in many cases, it's not as good as you think it might be. So, for example, it really does stop for about a second per live gigabyte. And the only thing you can do about it, other than using, is to delay that inevitable situation in your application, to lengthen the time between those events. But when people think that they can avoid it completely or they can change something in what they do, most of the time they're just pushing the problem forward. There are also memory leaks. If you forget to forget your objects, they're around. There's an entire class of memory leaks that goes away, but there are classes of memory leaks that remain. This is not a magic bullet against memory leaks. And one of the fundamental things that GC introduces as a new problem almost to most environments is that tuning garbage collection is usually not an exercise in improving performance, but in delaying bad things. That's not a normal tuning exercise for other platforms. So when you get a job to make your application run for 30 minutes sustained in this ramp with this SLA, and you pass or fail based on whether that happened, and you fail the first time, so you tune, and you fail the second time, you tune a little better, a little better. When you're tuning garbage collection, most likely what you did by passing a 30-minute test is not make a fast system that sustainably runs, but you just push the big bad thing to minute 31. That's the common exercise in tuning. You need to keep that in mind as you're tuning, because if your goal is to run for a week or a day or 5 hours without a problem, you shouldn't believe that the problem is gone just because you can't see it in this window. So let's talk about some terminology. How many of you know what a concurrent collector is? How many of you know what a parallel collector is? Fewer people. Okay. This is why we talk about terminology. So let's define them. A concurrent collector is a collector that does its job while your application is still running, without stopping your application, concurrent with your application. A parallel collector is a collector that uses more than one thread to do its job. These two terms have nothing to do with each other. They're orthogonal. You could be concurrent, but not parallel. You could be parallel, but not concurrent. You could be both. You could be neither. In reality, most concurrent collectors these days are also parallel, but there's plenty of parallel that are not concurrent. Other terms to define. Other terms to define, stop the world. Well, that's the opposite of concurrent. The part of your collector that's not concurrent will stop your application in its tracks and stop the world. Incremental generally means I have a big job to do. I don't have to do it all at once. I can do a part and then let you run safely. And then I can stop you into another part and let you run safely and stop you into another part. The opposite of incremental is monolithic. All at once. One thing, not safe to stop in the middle. Okay? There's another key term. Right? It's a term it's a pretty clean English language term. It's mostly. Mostly means exactly what it means, but you need to read it right. Whenever you see mostly in a sentence, that's like a not sign. Mostly concurrent means sometimes stop the world. Mostly parallel means sometimes serial. Mostly incremental means sometimes monolithic. The word mostly is really important because we use it a lot in garbage collection definitions. We usually use it to make the good thing look good and people ignore that. Other terms, precise versus conservative. Luckily, everything we deal with in Java these days is precise or exact. A conservative collector is a collector that doesn't quite know where all the stuff really is, doesn't know where all the live objects are, doesn't know where all the references are, doesn't quite know maybe whether a place in memory is a reference or an integer. And without knowing that, it's limited in what it can do. It needs to keep things alive that it's not sure about and has some limitations. A precise collector is the opposite. It's a collector that knows where all the pointers are and whether or not they are pointers at any point in time where it might need to collect. A collector has to be precise if it is going to move objects. The reason that's important is if you're going to move an object from point A to point B, you then need to find the 3 billion things that might point to it and fix those pointers before somebody sees them and uses them in the wrong way. It's hard to do if you don't know where they are, or if you're not sure if this is an integer or a pointer, and it might be just an integer that looks like a pointer because it has the same value. So preciseness is important. It's not the garbage collectors that makes things precise. They just have the easy job. It's the compilers, the JIT compilers, that need to provide all this information that says, at this point in the code, these are the references on the stack, and at that point in the code, here they are. So a lot of information compilers generate, and when they don't generate it, you do not have the ability to do precise collection. This is why we need to really respect all those JIT compiler guys working on JVMs. Okay? They produce a lot of good things for collectors. All commercial JVMs that use precise collectors, all commercial JITs provide this information. And this includes OpenJDK, by the way, I should just say commercial. That means that they all have some form of removing collector. Save points, I'll go through these quickly. A GC save point is a place in the code, a region of the code, a range of execution, where we actually have that information about where all the things are. We don't have to have it everywhere, but we need it at save points. And save points are the places where it's okay to run a garbage collection scan, supposedly on your thread or on something else. There are other kinds of save points, not just GC save point, for example, de-optimization save points and deflation save points. But we often conflate the two. GC save point and save point, I use them interchangeably. Bringing a thread to a save point means getting it to run up to and not past the save point. And I carefully choose my words here, because it might sound like I'm saying stop the thread at a save point. That often does happen. But a key example of not stopping at a save point, but just bringing it to a save point, is running into JNI code. When you're in native code to a JNI call, the entire code is at a save point. There's nothing you can do in that code to modify the Java state and make it different than what it was at the entry. You could be in there inverting the matrix in C++ code for an hour, and you're in a save point. Okay? It does not mean idle, it does not mean stall. All stall are safe points, but the other way around isn't true. You need safe point opportunities to be frequent, otherwise you'll get one of those situations where when you want a global safe point, meaning I need everybody to stop because I'm going to do some big thing that changes behavior. And this one guy hasn't run into a safe point part of the code yet for a minute. Well, everybody stopped and they're waiting for that guy. No useful work is yet done in the safe point. So that's I call that effect time to safe point. It's something at Azul we track a lot. We actually profile for it. And often it's the hidden cost of GC pauses or safe pointing that causes problems, not just the work of GC itself. That only happens once you reach the safe point. Here are some things that are common to all GC mechanisms. Every one of them will identify all the live objects in the heap, or at least the part of the heap it's responsible for. Every one of them will reclaim resources held by dead objects. That's almost the definition of garbage collection. Every single one of them will at some point relocate objects from point A to point B. It's not a lot of point in being a precise collector if you don't do all three of these. And let's go through examples of that in common practice. A mark, sweep, compact collector, a very common classic way of collecting. Mark is the first point, sweep is the second point, compact is the third point. However, a copying collector, commonly used in young generation collection, is all three in one pass. There's no separate stages here. A copying collector will take the from space, Eden or whatever the from space is in Mugen, and say, I'm going to find all the objects here, and as I find them, I'll just move them to a 2 space. That's reclaim, that's periodically relocate and find live. And when I'm done, well, I've got a big empty from space, and I can just reclaim it. And that's done generally as a single pass, not as a multi-pass operation. So all three things will happen. The algorithm used differs in how we have. So let's break it down into some pieces. Marking, also known academically as tracing. You start from what we call the roots. These are static variables, the contents of your threads. If you think of the threads as not roots, as roots actually, so obviously the point of that is a root. And other things that are, you can get to without having to find an object first. And you start from those, and you kind of go around painting any pointer you can reach through, getting to the next object, and then looking in there for other pointers to other objects. And you paint anything you can reach with pointers. If you've already reached something that's painted, that's fine, you don't have to look at it again. You kind of see what's reachable. And at the end of a scan, like that, anything that I reach will be marked live, as I said I could reach it. And anything I didn't mark live is by definition not reachable. And because it's not reachable, it will never again become reachable. It's impossible to make a non-reachable object reachable again. And therefore it's dead. It's safe to reclaim, recycle, whatever mechanism you want to apply to it. It's important, and I'm going to talk about complexity here for each of these stages. The work involved in doing this is linear to the amount of live stuff, live objects and references. That's what I have to do. It doesn't matter how big the heap is. It just matters how many things I'm following. So it only grows and shrinks with the live set. Sweeping, the second stage of a mark sweep compact. Imagine that we've marked. Sweeping is pretty simple. You scan through the whole heap, start at the beginning, go through the whole thing, maybe barrel, maybe not. And if you find something dead, you just recycle it somehow, usually by putting it on some sort of free list. Okay? Now we have a bunch of free places to put objects in the future. The complexity of this is simple. It's linear to the size of the heap, not to the size of the live set, the size of the heap, because I have to scan the entire heap to sweep. Compaction. Now this is an interesting one. Over time, the memory will get Swiss cheese, will get holes in it, and variable allocations at different places at different sizes, to the point where even though we've swept and we found empty things as we do that, I may have 90% of the memory empty, but no room to put my 10 kilobyte array. At which point I have a problem. Most JVMs don't like to break arrays into pieces, so we need to make a hole that big. And making a hole that big invariably moves objects. That's the reason we compact. Now, I get a lot of questions from people, well, is it really inevitable? Does it really happen? And the answer is, it's not actually inevitable. If your program has a fixed number of types of exactly the fixed size and a fixed pattern, then it may not happen to you. How many of you process XML? You don't have fixed size objects. You don't control the object size. It comes in and determines itself. And that's why your heap will get fed. And there are a lot of other examples of that. Compaction moves the live objects together to retain the contiguous space, and I call that relocation, the actual movement of the object. But the actual hard work is correcting all the pointers to those objects we move. I move one object, I need to scan everything that might point to it to fix it. That's why I don't move one object. We move as many objects as we can to amortize the scanning of all the things that might point. And generally that means move the entire heap, or in some incremental cases, move a set of regions that I could contain in each one. So remap, fix up, is the harder part, okay, the bigger part. And remap has to scan everything that might possibly point, not just the thing that really points, because it doesn't. Complexity-wise, as complex as this seems, this is still just linear to the live set, not the heap size. I only have to move live objects, and I only have to scan references in live objects. Okay? A different algorithm, separate from Mark's sweep compact, is copy, and I touched on a little on how that works. The copy collector moves things from the from space to the to space, generally starting from roots. And everything's in the from space, and then we take anything we can reach and we move it to the to, and anything it reach, we move it to the to, and it's all one pass. There's no rejiggering with this. And at the end of that, we started from root references, and we end with everything in the to and nothing in the from, and leave it plain off. The space, complexity-wise, linear to the live set. I only have to visit live object. Question there?
So isn't really from to is the copy, or they just swap the label?
So for this specific pass, the question was, is it really from to, or is it just the label? Right now, for this collection, that is the from and that is the to. And later, probably this will be the from and something else will be the to. Whether it's swapped or recycled or there are 15 of them, that's an algorithm question. So copy collectors do this, linear to live set. Let's put these together a little and compare and contrast. Copying has an interesting limitation where, since I'm copying everything from the from to the to, and I don't really know when I start how much is alive, how much is dead, I have to have as much to as I have from. It is not safe to start, because this is usually monolithic, and I can't go back. To start a copy without knowing that I can finish it. Knowing I can finish it means if I didn't collect even one thing, I will still finish the copy. Or I will have to crash your JVM, which is not a good thing. That's an interesting problem or limitation. It's costly. Mark compact without the sweep generally requires the same 2x, but there are interesting ways around it. However, it requires that I want to do it in one cycle, but mark compact generally can be stopped at any point in the middle, so it's more resilient to that. If it doesn't have 2x in memory, you can do something. Mark sweep compact, or compact in place, this is where you just move all objects to the left, but not to somewhere else, doesn't need 2x, it just needs 1x. It's a lot more memory efficient as far as worst case conditions are safe. Copy and mark compact are both linear to the live set and only to the live set, but mark sweep compact is also linear to the heap size. Very important quality you'll see in a second. And then mark sweep and sometimes compact might be able to avoid compaction for a while. It's a common trick. And copying, I already said, is monolithic. Okay, so let's talk about some ways to use these metrics in efficiency. Remember I said, copy is linear to live set, sweep is linear to the heap. Generational collection leverages an interesting observation, that is that most objects die young. It's called the weak generational hypothesis. It's not that old, unintended.